This is worksheet 6 of the States of Matter packet, and here we are going to sort of finalize and formalize ranking the strength of all the different bonding forces that we've talked about. And also talk about the results of these strengths, relative strengths, in terms of melting and boiling points. So we need to recognize that when we melt or boil a substance, so when we change matter from solid to a liquid or from a liquid to a gas, what we're actually doing is breaking the forces, the intermolecular forces between molecules in the substance, right? Because with a solid, the molecules are really held closely together. If you start to break some of those intermolecular forces holding the solid together, that frees up the molecules to move a little bit further apart, move a little bit more, slip and slide past each other. Now you've got a solid. If you keep adding energy, heat energy, and breaking those intermolecular forces even more, now those molecules can move even farther apart and move even more sort of rapidly, and now you have a gas. Okay, so because of this, the stronger the intermolecular forces that are in a substance, the more energy it's going to take to melt the solid or boil the liquid. All right, the stronger the forces, the more energy it takes to break them. And so things with really high melting or boiling points have really strong intermolecular forces. Things with really low melting or boiling points have much weaker intermolecular forces. So we have this sort of chart here, and over on one side we have the highest melting and boiling points, so those would be the strongest forces. Okay, I'm going to write as well as I can on this worksheet. It's really hard to do though. And over here are the lowest melting and boiling points, so these are relatively weaker forces. Okay, so if we start, first of all, we need to keep in mind that the very strongest are going to be all the intramolecular forces. Right? And I think if I scoot this, I can actually write a little bit better. So I want to give you some examples here. Okay? An example of a metallic bond, we didn't really talk specifically about these in our bonding packets, but our metallic bonds are just these attractions between metal atoms. So if you have gold jewelry, for example, right? So gold is Au. What happens is you've got all these gold atoms sort of floating around, attracted to the positively charged gold atom. That nucleus is attracted to the electrons of the other gold atoms, and so you have sort of like this sea of attraction between the positive center of the atoms and the negative electrons of the atoms, and it creates this really strong attraction between positive and negative. Okay, the same would be in aluminum. Yeah, that'd be another example of a metallic bond. Right, so it takes a huge high temperature to melt gold or to melt aluminum. The next sort of highest melting point in terms of the strength of the intermolecular forces would be an ionic bond. So we could think of salt, NaCl. Okay, it doesn't take much to dissolve salt in water, but if you wanted to actually just put salt crystals in a pan on your stove, you'd never get your stovetop hot enough to melt those salt crystals. So they have very strong attractions between the positively charged sodium and the negatively charged chlorine. Same with rust. Fe2O3 is rust, right? You get some rust on your car, you're trying to get rid of it. There's some options, but melting it off is not going to be one of them. All right. Next is the weakest of our intramolecular forces, the covalent bonds. So butter is actually a really complex molecule made of a lot of different covalently bonded compounds, but it's mostly carbon, hydrogen, and oxygen bonds. They're all all these atoms are sharing their electrons. So, you know, if you think about it, butter is going to be a lot easier to melt than like salt or aluminum. Okay, then we move to our intermolecular forces. So of the intermolecular forces, the hydrogen bond, the special type of dipole-dipole, is the strongest. So, for example, the bonds between water molecules. Okay, now water is liquid at room temperature. Okay, so everything else that we've talked about so far that has stronger bonding in it is a solid at room temperature. Right? I mean, butter kind of starts to melt into a liquid at room temperature. It's right on the border. But water now is actually a liquid at room temperature. So that's already an indication of the relatively weaker connections between those molecules. Okay? And if we want to boil it, we can put it on the stovetop and we can get it boiling, just with the temperature we can get on a stovetop, unlike salt, for example, or gold that we couldn't melt on our stove. Then our dipole-dipole, so that would be like carbon dioxide. Okay, now carbon dioxide, it's not even liquid at room temperature, right? We've already reached its, you know, boiling point, basically, so it's already a gas at room temperature. And then even weaker yet, okay, so it's oxygen. Okay, so you could pick a temperature, it'd be well above room temperature, where carbon dioxide was already a liquid, but oxygen would still be floating around as a gas, because those dispersion forces between oxygen molecules are the very weakest of all. All right, so you can kind of see the progression, right? We've got, with these really strong intramolecular forces, solid at room temperature. Then with our relatively strong but still intermolecular forces, we've got a liquid at room temperature, and then here we've got our gases at room temperature, which are the very weakest and easiest to melt and boil. All right, so I want you to kind of combine those ideas to answer question 1, and we can talk about that when you get to class. Okay, I'm going to show you an example of how you're going to do question 2, and then you'll do the rest. Okay. If you compare sodium chloride and ammonia, right, sodium chloride would be an example as a metal and a nonmetal. So that was actually our salt example here, right, of an ionic bond. I'm just going to make a little note of that before we write our full sentence explaining what we're going to talk about here. And ammonia, we have to look at a little bit closely. Ammonia, if we want to know what sort of intermolecular force would be holding two NH3 molecules together, we're going to have to go back and look at worksheet 3 at our electronegativity table. And we're going to see that nitrogen, N, has an electronegativity of 3, while hydrogen has an electronegativity of 2.1. And so the difference is 0.9. Now we're going to go to worksheet, make sure I have the right number, worksheet 5, right, where we have our bonding forces chart. And we're going to look in the intermolecular forces column, and we're going to see that that falls in, 0.9 falls in that range between 0.5 and 1.69, which means that this is a dipole-dipole bond, and specifically because hydrogen is in it, it's a hydrogen bond. Okay, so NaCl is an ionic bond, ammonia is a hydrogen bond, so which one is going to have the higher melting or boiling point? Well, it's really asking what's stronger, a hydrogen bond or an ionic bond. And it is indeed the ionic bond. Right, so, oops, ionic bonds. I circled sodium chloride. You could write out sodium chloride if you wanted, but I'm going to write out my explanation. Ionic bonds are stronger than hydrogen bonds. So it's going to be harder to break the bonds and either melt or boil this substance. Okay, so you can do a similar thing for part B and randomly part E. I don't know why that's not part C. All right, last thing to talk about, right, down here you got this table, and it's giving you some information about these different compounds. Okay, so you've got hydrogen gas, so that'd be H2, oxygen gas, O2, nitrogen gas, N2, right? I mean, you don't really have to know these formulas, honestly, but what it's saying is, okay, like if we look at the example of ethanol, right? It's saying the melting point of ethanol is negative 114 degrees Celsius. So that means at less than negative 114 degrees Celsius, if you could even imagine that, this would be a solid. And once it reaches negative 114 degrees Celsius, it melts into a liquid. This is alcohol, right? And then once it gets up to 79 degrees Celsius, so 25 degrees Celsius is room temperature, so this is pretty well above room temperature. That's its boiling point. So higher than that, it would be a gas. Okay? So it wants to know, all right, at room temperature, and sorry, I said room temperature was 25. I guess here we're saying room temperature is 22 degrees Celsius. Fine. It wants to know, what would it be? Okay, well, at 22 degrees Celsius, right? 22 degrees Celsius is going to fall somewhere in between negative 114 and 79, and so it's going to be a liquid. Ooh, and I'm noticing a typo. This should say it's going to be a liquid at room temperature. And so that's why I've written this here. Okay, so we could look at one more example, and you can do the rest together. Okay, the melting point of hydrogen is negative 259. This is crazy. So below negative 259, it's a solid. Starting at negative 259, it's going to melt and become a liquid. And at negative 252, much colder than we could ever imagine, hydrogen is going to boil. Weird to think about, right? And it's going to become a gas. So at 22 degrees Celsius at room temperature, well, 22 degrees Celsius is way higher than negative 252. So it's definitely going to be, by the time we get to 22 degrees Celsius, a gas. And some of you might know that hydrogen is certainly a gas at room temperature. All right, so I want you to go ahead and see if you can work on the rest of this chart, and we will discuss your answers the next time we are in class.